The next reaction we're going to discuss is epoxidation. And just as we've seen in the last couple of reactions with alkenes, reacting with halogens or reacting with mercury acetate, right? So in the reaction of halogens, you form halonium ions. It's a three-membered ring. In the reaction of mercury acetate with alkenes, you form that mercurinium ion, again a three-membered ring. Well, we can also react alkenes with electrophilic oxygens to form epoxides, three-membered rings with an oxygen in them. Now, in order to do that, we have to think about a possible source of electrophilic oxygens. And if we recall, a carboxylic acid, the oxygen on that carboxylic acid withdraws electron density away from the hydrogen. Well, we can think about what's called a peroxy acid, where instead of the oxygen bonded to a hydrogen, the oxygen is bonded to another oxygen. Now, why is this of interest to us? If you recall, a carboxylic acid is very acidic. Why? Because the oxygen is withdrawing electron density away from the hydrogen, and it makes that hydrogen acidic. It also makes it electrophilic, right? So that it can be removed relatively easy. So just similar to that type of scenario, we have a peroxy acid where the oxygen connected to that carbonyl is going to withdraw electron density. But it withdraws electron density away from another oxygen this time, and it makes that oxygen electrophilic in nature. And so that's going to be an important concept when we react it with an alkene. So what happens? Well, let's start off the bat thinking about the mechanism of this reaction, because it's a simple one-step mechanism, a concerted mechanism, but there are a lot of arrows involved, and so we have to kind of keep track of what's going on. So here I have a generic alkene, and I'm going to react it with the peroxy acid. Now, I'm reacting it with that the oxygen on that peroxy acid. So what I'm going to do is I'm going to orient the peroxy acid like this. It makes it a little bit easier. So the blue oxygen is going to be the one that inserts itself into the alkene, creating a three-membered ring, a carbon-oxygen-carbon ring. How does it do so? Well, like I said, it is electrophilic, right? Electron density is being withdrawn from it. And so the first step is the pi electrons attack that oxygen. Now, what happens is a series of events, and so the next step is that we can get back donation, just like we saw with the alkene reacting with a halogen, just like we saw with an alkene reacting with mercury acetate. And we get a bond breaking. So an oxygen-oxygen bond is going to break. It's the weaker bond. And those electrons are now going to go form a pi bond between the yellow oxygen and the carbon. But if that's occurring, now that carbon has too many electrons, and so a pi bond from the carbonyl is going to remove the proton off of the peroxy acid. And then the electrons from that oxygen-hydrogen bond are going to go to the oxygen. So we have 5 arrows here, and as long as you think about, the process and the similarity between this and the formation of the halonium ion or the formation of the mercurinium ion, you can see the patterns emerge. And so the result is, let's see if we can follow this. Okay, so my red arrow created a new bond to oxygen. The oxygen donated its blue electrons to the pi system. So now I have my epoxide, right? So that's my epoxide. I have a pair of electrons that weren't involved in anything, and then I have a new pair of electrons that are coming from the oxygen-hydrogen bond, so I've colored them red. And then I have this the result of what's left over on my on my peroxy acid. So let's think about what happened here. So the oxygen has two lone pair of electrons that weren't involved in anything, and it also created a new pi bond, right? From the oxygen-oxygen bond breaking, the electrons went to form a pi bond. The other oxygen has now a new oxygen-hydrogen bond, and so this is our product. We form an epoxide, also called an oxyrane, if you recall, and the byproduct of this reaction is a carboxylic acid. So let's look at a reaction. A simple reaction is where we take an alkene and we react it with a peroxy acid. So this is the way a peroxy acid would look like. This is peroxyacetic acid. So acetic acid is CH3CO2H. Peroxyacetic acid is CH3CO3H. You need to recognize that and be able to draw the Lewis structure of that as well. Okay, because if I asked you for the mechanism of that reaction, you'd certainly have to know how to draw the Lewis structure. But the product of this reaction is simply an epoxide. Obviously, we get acetic acid as a byproduct, but we typically don't draw acetic acid as a byproduct because the focus is on the functional group transformation. An alkene is going to an epoxide or an oxyrane. Okay? All right, so a couple other variations of this reaction. If I start with an alkene that has particular stereochemistry, so for example, I have a cis alkene structure here, and I react it with MCPBA in dichloromethane. Now, MCPBA is a very common peroxyacetic acid. MCPBA is this structure right here, right? So this is a derivative of perbenzoic acid. Benzoic acid is the benzene ring with a carboxylic acid. So this is a peroxy acid, so it's a perbenzoic acid. And there's a chlorine on the benzene ring that is in the meta position, and so this is referred to as metachloroperbenzoic acid. And obviously, it's abbreviated often as MCPBA. So MCPBA. When you see MCPBA, you need to recognize that that is a peroxy acid. Now, the outcome of this is that peroxy acids form in a syn addition. Obviously, that has to form in a syn addition because you're only adding one thing across a double bond. And so the product of this reaction would simply be this. Obviously, this is a meso compound in this particular example, and if I were to react the trans isomer of the alkene with MCPBA, I would get a racemic mixture of two enantiomers. So, for example, I can react a cycloalkene with, this is trifluoroperoacetic acid, and I get an epoxide from this. So the epoxide, the oxygen can be either above the plane of the board or below the plane of the board. So I can get either this isomer or its enantiomer. So I get a racemic mixture of this product formation. Now the cool thing about epoxides is their reactivity. And so if you think about epoxides, they're much more stable, obviously, than halonium ions or mercurinium ions, and they're easily isolated. The reason for this is because they're neutral compounds, and so you can isolate epoxides relatively easily, whereas you can't really isolate halonium ions, and you can't isolate mercurinium ions that well. You can, but we typically don't because it's followed by hydrolysis. So even though they're more stable, epoxides are more stable than halonium ions, they can undergo ring opening reactions in both basic and acidic conditions. And we're going to see some regiochemistry play out in either basic or acidic conditions. So let's take a look at what's happening in those two types of reactions. So we'll focus on a basic reaction first, and we're going to simply take a look at the hydrolysis um, of ethylene oxide. So I'm going to take ethylene oxide and react it with hydroxide in water. This is a hydrolysis reaction, and what's going on here? So the key features of this reaction are twofold. Epoxides can behave as both electrophiles and as nucleophiles. So the key is in recognizing the reagents. Again, it's important to recognize reagents. So here I have hydroxide. Is hydroxide an electrophile? Absolutely not. Hydroxide is a nucleophile, and therefore the hydroxide is going to attack the epoxide, and the epoxide is going to behave as an electrophile. So how is it an electrophile? Well, the oxygen withdraws electron density away from the carbons, and the carbons become then electrophilic in nature, so that my hydroxide ion can attack the one of the carbons, and obviously in this case it doesn't matter which carbon. We're going to see later on that when you have an asymmetric or unsymmetric epoxide, it will matter. And so now once the hydroxide attacks the carbon, it opens up the ring in a standard SN2 substitution, notice. And therefore that's important to understand that this mechanism is an SN2 mechanism, so steric effects are going to become important. So the result of this looks like this. The epoxide now has opened up, the oxygen has a negative charge on it, and the carbon on the right-hand side has an OH group, so a typical substitution reaction. And now I simply can protonate the alkoxide that forms with water, because we're in aqueous conditions. I regenerate hydroxide in the process, and I end up with two OH groups across that are vicinal to one another. So we call these vicinal diols. So we're forming alcohols. They're di-alcohols, or simply diols, and they are vicinal to one another, vicinal diols. Okay? All right, so that is basic conditions. Basic conditions, you're reacting, the base is a nucleophile, and so the nucleophile, the base, attacks the epoxide. But what happens in acidic conditions? In acidic conditions, again, we have our epoxide, and so now we're going to react it with aqueous acid, right? So the hydronium ion. And in this case, the epoxide is a nucleophile. Now, how is it a nucleophile? The oxygen is electron rich. It's behaving as the nucleophile. Hydronium ion is always an electrophile. And so what we're going to do is we're simply going to protonate the oxygen. And so we get proton transfer to occur, and the result is now our protonated epoxide. Now, what have we done there? Well, basically, we've made a good leaving group, right? Just like in substitution reactions, now the oxygen can leave relatively easily, and we don't need as strong of a nucleophile. Water certainly works as a nucleophile. It can attack the carbon, open up that ring, right? And we're left with this product, right? So now we have an OH on the right-hand carbon, and on the left-hand carbon, water has attacked. So now we're forming the oxonium ion, and now all I have to do is deprotonate that oxonium ion with water. And of course, we have seen this a million times by now, how to deprotonate the oxonium ion, and the result looks like this. And so you should be saying, wait a second, this is, what does this structure look like? Well, it's a vicinal diol. So it's the same vicinal diol as we saw in basic conditions. So the hydrolysis of an epoxide in basic conditions and in acidic conditions yields the same product, right? But now let's take it a step further. What happens selectively when you have an epoxide that is unsymmetrical? So now I have an epoxide where, let's say, I have an R group coming off of the epoxide, and on the left-hand side, doesn't really matter, arbitrary, and on the right-hand side I have two hydrogens. Well, in acidic conditions, so I react this in acidic conditions with some type of nucleophile, and the result is that the nucleophile always adds to the more substituted carbon. Whereas in basic conditions, right, so now I have some negatively charged nucleophile. When I react this nucleophile with my unsymmetrical epoxide, the nucleophile always adds to the less substituted carbon. Why is this? Well, recall in basic conditions, it is an SN2 mechanism. And so this is going to be driven by steric effects. So in basic conditions, the green scenario, right, where I have a basic nucleophile, it's going to add to the least hindered carbon, opening up the ring to form an alkoxide, and then you get a proton transfer of that alkoxide, right? However, in acidic conditions, what's happening? We're protonating, typically. We protonate the oxonium ion, and the behavior resembles that of the halonium ion, where the next step is a nucleophile comes in, and it comes in to attack the most substituted carbon, right? So if you see the parallels between the mechanism of the halonium ion and the mercurinium ion and that of the epoxides, then it makes it a little bit easier to understand what's going on. All right, so let's look at a couple of examples. In the first one here I have an epoxide, and I'm going to react it with sodium cyanide in water. So the first step is to recognize, is this basic conditions or acidic conditions? Well, sodium cyanide is not an acid, right? Cyanide is an anion. So I don't have an acid present, and therefore the key is recognizing, okay, this is in basic conditions. What's the first thing that's going to happen? Well, the first thing that happens is my cyanide ion, and again, I have to think about the Lewis structure of the cyanide ion, thinking about the connectivity of it. So that cyanide ion is going to attack the epoxide. Where is it going to attack? It's always going to attack the least substituted carbon because it's a simple SN2 mechanism. So I'm going to attack the carbon on the right side, opening up the ring, right? I form my alkoxide, and then water can come in and protonate it, and I form this product, right? So cyanide has added to the least substituted carbon, and the other carbon is the alcohol, right? These are called vicinal cyanohydrins, right? So similar to vicinal halohydrins, we have vicinal cyanohydrins. All right, so what happens if I react, let's say this epoxide, where I have on the left-hand side my carbon has an ethyl group and a methyl group, and on the right-hand side my carbon has two hydrogens, and I'm going to react it with HBr. Is it acidic conditions or basic conditions? Hopefully by now you can figure out this is an acidic condition. So what's going to happen? The oxygen of the epoxide is going to get protonated, and now the bromide is going to attack the epoxide, or the protonated epoxide. Where is it going to attack? It's going to attack the more substituted carbon. And so the product looks like this, right? So the bromine has attacked the carbon on the left-hand side, and you get CH2OH on the right-hand side. Remember, this is going to be via protonated epoxide, where it looks like this, right? So now I've protonated my epoxide, and bromide's going to come in, and it's going to attack the left-hand carbon because it is the more substituted carbon, and you open up that ring and you get the product. And of course, this is going to be a stereo specific reaction, right? Because the bromide ion can only come in one direction, and we end up only with one particular enantiomer. And so this is also called a stereoselective reaction as well. So we have stereospecificity, stereoselectivity in this reaction. Okay. Now, one of the things that we have certainly talked about in the past is organometallic reagents. And we're going to bring these up again because organometallic reagents are nucleophilic, right? They're bases and they're also nucleophiles. So recall organometallic reagents are Grignard reagents and organolithium reagents. And so we can treat epoxides with Grignard reagents or organolithium reagents. For example, if I take this particular epoxide and I react it with methyl magnesium bromide in THF, what's going to happen? Well, again, we have an unsymmetrical epoxide and we have a Grignard. Is the Grignard an acid or is it a base? Grignards are always basic, right? They're good bases. So what's going to happen when my Grignard, methyl magnesium bromide, reacts with the epoxide? Where is it going to attack? It's going to attack the least substituted carbon and undergo an SN2 reaction. So it attacks here, opens up the ring, and you form an alkoxide, right? So now, obviously, we're going to need a second step. So in the first step, we react it with a Grignard. In a second step, we can follow that up with an aqueous acidic conditions so that we can get protonation of the alkoxide to yield an alcohol, right? So here we are making alcohols and we've also created a carbon-carbon bond. So this is a very important reaction. Whenever you can form a new carbon-carbon bond, that makes it kind of a special reaction. We're basically extending the carbon skeleton and creating a new functional group. So we've taken an epoxide and reacted it with a Grignard, extended the carbon chain, and made an alcohol. And now what can we do with that alcohol? Well, we can dehydrate it and make an alkene, and then we can take that alkene and we can, treat it with all sorts of things, bromonium ion, and make an alkyl, a vicinal dihalide. The possibilities are becoming limitless, right? So here's another reaction, just showing you I have an epoxide, I'm reacting it with an organolithium. So generally speaking, again, notice the first step is reacting with an organolithium, the second step is aqueous acidic conditions. Why? Because if I simply reacted my organolithium in water, it's a strong base, it would be protonated. So I have to do this in two steps, okay? So I react it with the organolithium. I'm adding a propyl group. The propyl group is going to attack the carbon on the right, because it's least hindered, SN2 substitution, and my product is this, right? So I've added that propyl group to the carbon on the right, and then the carbon on the left, it forms the alkoxide. That alkoxide gets protonated. Now, one thing that we're going to learn about Grignard reagents and organolithium reagents is they're fairly reactive to a number of functional groups. So they react with epoxides. They also react with functional groups like ketones and aldehydes. So one way of using a milder organometallic reagent is to use what's called an organocuprate. So organocuprates work well opening up rings, and the other key component to this is they don't react with other functional groups like ketones and aldehydes. What is an organocuprate? So an example of an organocuprate is this, R2 copper cyanide Li2, lithium 2, right? So it's a kind of a complex structure. So the R2 can be essentially any alkyl group. There are two of them on there. We're going to talk about organocuprates later on in more detail, but in essence, what you need to understand is that this reagent here simply transfers a carb anion, right? So for the time being, I just want you to recognize that when you have an organocuprate like this, it's going to transfer an R group to the epoxide. So for example, here's my epoxide. I'm going to react it with dibutyl copper cyanodilithium. Okay, dibutyl copper cyanodilithium in THF, followed by an aqueous workup. What's the key? The key is to recognize, okay, C4H9, that's a butyl group. It's simply a butyl chain. So I'm going to add that butyl chain to the least substituted carbon. It behaves the same way as a Grignard reagent does. And so my product is this, right? Now, the key is for organocuprates is being able to react and extend the carbon chain, reacting an epoxide in the presence of something like a ketone. So if I were to use a Grignard or an organolithium reagent, it would react with both the epoxide and the ketone. If I react this particular structure with dimethyl copper cyanodilithium, then all I get is the reaction of that with the epoxide. And so I'm simply adding a methyl group to that structure and forming my alcohol. So that's a kind of a key component to this particular reaction. And the last thing that we want to talk about in terms of reactions, ring opening reactions of epoxides, is the reaction of hydride reagents. So we've seen hydride reagents before. Sodium borohydride is a hydride reagent. Another hydride reagent is lithium aluminum hydride. And what happens is if I take an epoxide and I react it with sodium borohydride in water or methanol, something like that, the hydride transfers. Now again, hydrides are basic, okay? So the same rules apply in basic conditions. I'm going to transfer a hydride to the least substituted, so that would be the carbon on the bottom there, and open up that ring, and I get this as my product, right? I can also use lithium aluminum hydride. Now, lithium aluminum hydride is a little bit more reactive than sodium borohydride, so we typically can't run reactions of a lithium aluminum hydride in water or alcohols. So we have to run them in ether and then follow that up by reacting it with in aqueous acidic conditions to protonate the resulting alcohol. And so the product simply looks like this. Now you may go, well, how does that mechanism work? Your textbook really doesn't talk that much about the mechanism at this point, but I do want to highlight we've seen the structure of borohydride in sodium borohydride. This is the structure of aluminum hydride. It looks very similar, except you have aluminum instead of boron. The aluminum has a negative charge. So these are hydride donors. So what's going to happen is my H aluminum bond is a relatively weak bond. The aluminum has a negative charge, high electron density, and so it attacks that least substituted carbon, the least hindered carbon, opening up the ring. And so notice I'm transferring a hydrogen onto that carbon, and then I get an epoxide. And now at this stage, I can treat that epoxide with water or the hydronium ion, and I get protonation. So that's how that mechanism works. And you see, it's very similar to the reaction of, let's say, a Grignard reagent or an organolithium reagent, right? It's just a hydride reagent. Now, the mechanism actually is a little bit more complicated than that because you end up getting these aluminum esters forming, but we won't go into great detail about that. All you need to know is at this stage that the aluminum hydride or borohydride transfers a hydride, and the result is you get an alcohol, right? Now, in this type of reaction, you're not extending the carbon chain at all, but it allows us to make, secondary alcohols, so that we have now a new type of pathway to making alcohols, right? So we've seen a lot of things that we can do in epoxidation. We epoxidize an alkene, and then we can do a whole bunch of ring opening reactions with the resulting epoxides.